Okay, quick announcement before we start the lecture. We're going to have a slightly different lineup this week of instructors. So we will not be holding the usual Wednesday 5 p.m. recitation section, but instead, Yi Zhang, who is going to give that recitation, will be giving it Thursday here during the class period. And that'll be a chance. It turns out I need to be out of town on Thursday, so he is going to do the recitation here at the usual Thursday class meeting time, and he'll cover some material and also give us a chance to have a little bit more question answer than we usually can afford with a lecture style. So that's the plan for this week. So let's start. So we just finished really talking about logistic regression and naive Bayes. So we've just finished talking about the first two seriously probabilistic approaches to machine learning in the class, naive Bayes and logistic regression. So what I want to do today is take a look at those two in particular and ask the question, when might we want to use one versus the other? And then we're going to move on and introduce a third, again, probabilistically motivated learning algorithm. And by now you'll see it won't even take us that long because you already know the template for doing this. And we'll take a look at that. That's going to be linear regression, where the function we're trying to approximate has a real valued y instead of a discrete valued y. So that's the plan for today. Just to kind of swap us all back in, here's my one-slide summary of everything we've talked about linear regression. So again, the point of linear regression is that we're trying to learn some function from x to y, or equivalently, the way we think about it, the conditional probability of y given x. And if we make assumptions very similar to what we make for Gaussian naive Bayes, plus this one assumption that the conditional distribution of the individual real valued features x sub I given y is Gaussian, but that if we make this additional assumption that the variance of those Gaussians is the same for every possible label, then we found that we could derive the answer to the question, well, what would be the form of p of y given x? And we found this was the form. And then we moved on and we talked about training the weights, the w sub i's, in this logistic regression form directly by maximizing the conditional likelihood of all the training example y values given the training example x's. And then when we wrote down the formula for maximizing the conditional likelihood, the likelihood of the y's given the x's and the w's, then we found that we could derive a gradient descent, actually gradient ascent, rule that allowed us to iteratively re-estimate those wi's until they indeed did maximize the conditional likelihood of the training example y's given the training example x's. And so that's our optimization procedure, or our training procedure, our way of fitting the training data or fitting the W sub i's to the training data. Okay, so that was logistic regression. And I just want to point out, and this is actually an important thing to realize, we had a little discussion about this after the lecture up in the front of the room last time. But if you ask, well, what are the assumptions in the logistic regression algorithm? Then the smart way to think about that is to break that down into two different questions. We can ask, what are the assumptions we made in order to derive this functional form, the logistic function, as the way we're going to represent P of y given x? And the assumptions we made there are precisely the ones that are on the top half of this screen. But then we could also ask a slightly different question, which is, what are the assumptions we make in the training algorithm itself? Once we're committed to this functional form, the training algorithm, that gradient descent algorithm, if you think about it, it's really not making anything like a conditional independence assumption. It's not making any assumption except that P of y given x is of this functional form, and then it's finding the W sub i's that maximize the conditional data likelihood, given really the only assumption it's making is that we're going to use this functional form. So there's a kind of interesting openness of the gradient descent training algorithm to violating the assumptions that we made when we were deriving this functional form. See what I mean? It's like, yeah, we made those assumptions when we derived the functional form, but once we had the functional form, our procedure for estimating the W sub i's really makes no assumptions except that we want to optimize the conditional data likelihood. So in that sense, logistic regression is a little bit more free and easy than Gaussian naive Bayes, because when you train the Gaussian naive Bayes classifier, you really are estimating these mu's and these sigmas, and you really are applying those to classify new examples under the conditional independence assumption. So that's part of the perspective that we're going to have to take if we want to understand what's the difference between logistic regression and Gaussian naive Bayes. Okay, so one reason that we're actually spending so much time on Gaussian naive Bayes and logistic regression is they're really exemplars of what people often call generative versus discriminative classifiers. And we'll see others as the semester goes on too. But for example, naive Bayes is an example of what people call often a generative classifier. And what they mean when they say that is that it's a probabilistic classifier that assumes some functional form for P of y and P of x given y. And therefore, and then it estimates those two things from the training data. And then it uses Bayes' rule to classify new x's to find the distribution of y's given a new x, the probability distribution on possible y's given a new x. In contrast, logistic regression is an example of what people call a discriminative classifier, by which we mean a classifier that just assumes some functional form for the conditional distribution of y given x, and then directly estimates the parameters of that without going through this Bayes' rule intermediate step. The reasons for calling these generative and discriminative are a little bit quirky, but roughly it's this. Logistic regression is called discriminative because it's not really, all it cares is what the y is. Given an x, it's just interested in discriminating whether y equals 1 or y equals 0. And in fact, if all you're learning is P of y given x, that's sort of the only question you can answer. On the other hand, naive Bayes is actually learning, in a sense, more than logistic regression is learning, because it's learning really the joint distribution of P of y and x. How can I say that? Well, because, of course, by the chain rule, the joint distribution is just the product of these two things. And these two things are precisely what naive Bayes is learning. So by learning those two probability terms, P of x given y and P of y, it's effectively estimating the entire joint distribution on x and y. And so in that sense, it's making more of a commitment. It's learning more about the probability distribution on x and y, whereas logistic regression is just learning this. Logistic regression essentially doesn't care what P of x is. It just says, give me an x, and I'm just going to tell you about P of y given that x. So that's really a big difference. And so one reason people call naive Bayes a generative classifier is that it's got enough information. It's got the whole joint distribution of x and y. And so it's easy, given a trained naive Bayes classifier, to generate examples pairs, x, y pairs, according to the distribution that we're training from. Sorry, let me say that a better way. Once we've trained our naive Bayes classifier, we have the joint distribution of p, y, and x. And it's easy to use that learned estimate of p of y, x to generate pairs, x, y pairs, according to that distribution. How would we do it? It's easy. We've got p of y and we've got p of x given y. So going back to our Squirrel Hill example, we just first we'll pick a y. Well, once we trained our Squirrel Hill naive Bayes classifier, we had a prior on y being 1 and 0. I can't remember what it was, but let's say it was 0.61 and 0.40. So with probability 0.6, we'll generate a y equals 1, and with probability 0.4, we'll generate y equals 0. Then, given that we've generated a random draw of that y, we'll just generate an x conditioned on whichever value of y we chose. And again, suppose we choose the value of y equals 1 on some draw. Then we'll go to p of x given y equals 1. And according to that distribution, we'll generate our x's. So it's a generative classifier in the sense that once we've trained it, we have enough information to generate random draws from p of x, y. And that's not the case, of course, for logistic regression. So there's one difference that's kind of interesting to think about. And so let's move on to actually the most fun question. When would we want to use one or the other of these? And the answer actually turns out to be pretty interesting. Sometimes it turns out we're going to want to use Gaussian naive Bayes. Sometimes we're going to want to use logistic regression. And it turns out the reason, the trade-off that we want to make, the basis for choosing one or another, is these two issues. One is, how restrictive are the modeling assumptions? Are we making conditional independence all the way through, assumptions all the way through, or not? Another thing is it turns out that these will have different learning curves. So if we have a little bit of data, the trade-off is going to look a little different than if we have, say, infinite amount of training data. And so these are two issues that are going to influence which of these methods we want to use. Okay, so to get some feeling for the first of those, the complexity of the modeling assumptions made by the system, let's go back to one of our old favorite questions. How many parameters are there in these? So suppose I'm training a classifier, both a Gaussian naive Bayes and a logistic regression, where I have a Boolean y and I have x1 up through xn real valued variables that x's that I'm going to model as Gaussian. Then how many naive Bayes, Gaussian naive Bayes parameters are there? Wow. Okay. We better figure this out then. For each, well, we need P of y. That just costs us one parameter, right? Because y is Boolean. And then we need n times a mu for y equals 1, and a mu for y equals 0, and a sigma for y equals 1, and a sigma for y equals 0. So we need 1 plus 4n. Right? Right? N being the number of, for each of these features, we need to estimate the Gaussian distribution conditioned on y being 1 and 0. It's 1 plus 4. And for logistic regression, how many do we need? N plus 1. That's easy to see because I wrote down the equation over here. All right. So one thing we notice is logistic regression involves estimating somewhat fewer parameters. That's kind of interesting. If all these parameters were independent, then that would suggest that somehow naive Bayes is more expressive or something. Okay, so that's one way we can think about it. But now let's consider the question of which one we would like. And I want to simplify the question by assuming that we have infinite training data. Okay, so there will be no risk that that one of these methods will work poorly because it didn't have enough training data and it's got high variance in the estimates of its parameters. Suppose we have infinite training data. Then which method would we like to use? Now, to be precise, I'm actually going to talk about 3 algorithms instead of 2. So let's just go down the slide here. Recall that when we derived the form of logistic regression, we really made 2 assumptions. The first was the conditional independence assumption that Gaussian naive Bayes always makes. The second assumption we made was this one that the sigmas really don't depend on y. We had to make that, well, we made that. And that allowed us to get this nice log linear form of the logistic function. Okay, so to make this discussion a little bit more well-formed, I'm going to talk about GNB, Gaussian naive Bayes, as just making the first assumption, the conditional independence assumption. But I'll introduce another algorithm we'll call Gaussian naive Bayes 2, which makes both assumption number 1 and assumption number 2. Okay, so in a sense, logistic regression is derived from the assumptions of GNB2, really, right? Because we added that additional assumption. Okay, so now, suppose I have infinite training data, and you get to choose one of those 3 learning algorithms to use. And I tell you that I'm going to give you infinite training data for some problem where assumptions number 1 and 2 really are satisfied. Really, they really do hold for this data set. Then what can you tell me about the relative accuracy of those 3 classifiers on future test data? Yeah? They'll be the same. And the reason is?
Well, all the assumptions hold, so the only types of errors you can make is the ones where it's like the type 1 and type 2 errors where it's a train, you just don't have enough error, like the variables are trained.
Good. So the assumptions are satisfied. That's what we agreed on. And therefore, let's take one of these GNB. Can it represent the optimal classification rule? Yes, because it's making those assumptions and they're satisfied. So there's some setting of the mu's and sigmas for GNB that will give us the optimal Bayes, well, the optimal classifier. And GNB, given infinite training data, if we give it maximum if we allow it to have a maximum likelihood estimates of mu's and sigmas, which are unbiased estimates, then it will get the perfect estimates for mu and sigma, and it will learn the best possible decision surface for classifying x's for which y equals 1 versus y equals 0. The same, of course, will be true for GNB2. It's making this additional assumption, but we've said that's satisfied too. So it will also learn actually exactly the same decision surface. It'll turn out to be a linear decision surface because assumption 2 is satisfied. GNB2 and GNB will learn the same linear decision surface. And so will logistic regression. Last time when we talked about logistic regression, we actually gave the formula for how you convert the perfect mu's and sigmas into the perfect w sub i's. And given infinite training data, that's exactly what the training procedure for maximizing conditional likelihood for logistic regression is exactly what it will do. Okay, so in this case, it turns out GNB has the same performance as GNB2, has the same performance as logistic regression. Okay, now what if I repeat this? Again, you get infinite data, but I say, well, sorry, neither of these assumptions is satisfied. Now what can you tell me? That's sad, isn't it? In this case, here's one way to think about it. Let's compare GNB and GNB2. GNB2 actually has fewer parameters than GNB, right? It's the one that's assuming the sigma sub ik's don't depend on the k, don't depend on the value of y. So GNB2 actually has a more restricted hypothesis space. The set of all decision surfaces GNB2 can learn is really just a subset of the decision surfaces that GNB can learn. In fact, GNB2 can learn only linear decision surfaces, whereas it turns out GNB, since it's not making that assumption, can in fact learn nonlinear decision surfaces. So given that, GNB actually is a more expressive learner in the sense that it can represent a superset of the decision surfaces that GNB can represent, GNB2 can represent. So in that sense, GNB is going to do at least as well as GNB2, because for anything that GNB2 can learn, GNB can learn it too from the same infinite data. But if the perfect decision surface is not in that subset of linear surfaces that GNB2 can represent, and it requires some nonlinear one that GNB happens to be able to represent, then it's going to win because it's going to learn that one instead. Right? So it has a bigger hypothesis space, a bigger model space. Okay? Anything else we can say? Here's one other thing I would claim. I would say logistic regression will do at least as well as GNB2 under a very similar kind of argument. So again, GNB2 can only learn linear decision surfaces, so can logistic regression only learn linear decision surfaces. But GNB2 is locked into this conditional independence assumption all the way through. And logistic regression, as we started out saying at the beginning of today's lecture, actually we only made that conditional independence assumption when we were trying to justify the form of the logistic function. But during training, our training procedure can easily violate that conditional independence assumption in the following precise sense. During training, when we're doing gradient descent on those different weights, our algorithm can violate the conditional independence assumption in the sense that once we have those final weights, there is no set of mu's and sigmas that would give us those weights according to the correspondence we derived last lecture. So logistic regression is locked into linear decision surfaces, but not the ones that GNB2 is locked into. It's sort of more flexible in that sense. So for that same reason that logistic regression has a more flexibility during training, I believe it will do the same as GNB2 if GNB2 can do well. But in other cases, logistic regression can learn a different linear surface. Okay, let's move on to this one. What if the conditional independence assumption is satisfied, but not our other one about the sigmas being independent of y? Then which one would you put your money on? G and B, so would I. Because now we know that the Gaussian G and B can represent the correct surface because this assumption is satisfied. And G and B doesn't make this second assumption. And that surface might, for example, end up being nonlinear. And logistic regression is locked into linear surfaces. So in this case, I'd say G and B will have to do at least as well as logistic regression. Okay. All right. So so that's our analysis in the case of infinite training data. And you see what we've really done is we've been arguing about how expressive is the hypothesis space or the model class, that's a synonym for hypothesis space, that these three different algorithms are using. And so, for example, in this case, we prefer GNB because we're told the modeling assumptions are satisfied, and we know it can represent a greater variety of hypotheses than logistic regression, which is restricted to linear surfaces. So that's the nature of the argument in terms of asymptotic analysis, meaning asymptotic with respect to the amount of training data we show the system. Okay. So you can see this is making it look like GNB is pretty good. Maybe logistic regression if we know something about, if we really trust those assumptions. Okay. Now, let's move on to the next question. What if we only have finite training data? So instead of infinite training data, I only give you 10 training examples, or 100, or 1,000, or 10,000. I'll give you n training examples. Does that change the picture? Well, it does because of this result. So let's go through this carefully. Actually, these different algorithms converge toward their asymptotic error rates at different rates. So I'm going to use the symbol epsilon to refer to the error. And epsilon sub a n is the error of algorithm A given only n training examples. And I'll assume these are n random training examples drawn from the true P of xy. So there is some, P of xy out there in the universe. We don't know what it is, but it's generating training examples. And we'll assume, so when I talk about epsilon for particular algorithm A and n training examples, what I really mean precisely is the expected error of when we train algorithm A on a random sample of n training examples taken from that underlying P of xy. Of course, if I repeat that experiment, let's set n to 10, if I repeat that experiment a bunch of times, first I'll draw 10 training examples and train and see what my error is. Then I'll throw that away and draw another random 10 and train. Of course, the error that I get will vary about its expected value. And I'm using epsilon to represent the expected value of that error when I repeat that training, just to be precise. Okay, so then here's the interesting thing. Wow, with a typo. Can you find the typo? So let's look at the top one, which has no typo. What this says is that the error that we'll get with logistic regression and n training examples is bounded by the error we would get if we had infinite number of training examples. Of course, logistic regression is not guaranteed to be perfect just because we have infinite data, right? We talked about that last time. If we have two Gaussians that overlap, I guess they'll need to because they have infinite extent. If we have two Gaussians that overlap, then the part where they overlap is going to give us this unavoidable error, even if we perfectly learn the decision surface that's best. And that'll be our epsilon for logistic regression for an infinite number of examples. That'll be if it learns the perfect decision thing. And there's still some remaining error. Then there's this other term which varies with the square root of d over n. And n, again, is the number of training examples. D is the number of features. So if we only have n training examples, we're going to get this unavoidable epsilon sub logistic regression infinity error. That's the unavoidable error. Plus another error that'll be bounded, that'll be on the order of, that will decrease with the square root of d over n. I'm sorry, that will increase with the square root of d over n. And so if I shrink the number of dimensions, I have fewer features, that'll work out better. In a way, I have fewer parameters to estimate if I shrink d. Or if I double the number of training examples n, then square root of d over n will also shrink as the square root of 1 over 2. Okay. And this is a result from Andrew Ng and Mike Jordan from a couple years ago. Interesting result. What's the case for GNB? Here's my typo. GNB suffers its unavoidable error that it would get also if we had infinite data, plus this other term. And this term only grows as log of the number of features instead of the number of features. So that's pretty cool. Why is it that we get this different behavior? Here's the reason intuitively. Once you see it, it kind of makes sense. Think about all these parameters that GNB has to estimate, and also all the parameters logistic regression has to estimate. Let's just consider GNB first. Let's take one of those, like mu for feature 4 conditioned on y equals 1. Okay, that parameter. Now, that parameter, the estimate that we have for that, doesn't depend on the other mu's. Right? We're getting maximum likelihood estimates of this, and they're all independent. So if I make a mistake because of variance in the data, in estimating one of those other mu's, it doesn't actually influence, it doesn't cause any kind of problem or mistake in my estimate of this other mu, because they're all independent estimates. I'm just getting these maximum likelihood, sample mean estimates for all the mu's. However, for logistic regression, all of these W sub i's, all of those estimates of all the W sub i's, they're all coupled in the following sense. If you train your logistic regression classifier on whatever data you have, and then I go in and I subtract epsilon from one of those w sub i's, and I don't let you change that, but I let you change all the other wi's to maximize the conditional likelihood, you'll change them. They're all coupled in the formula that we're using for doing that gradient descent. And because they're coupled, variance that sneaks in to cause error in one of those parameter estimates kind of trickles through to potential error in other estimates. Whereas we don't get that effect for naive Bayes because all the parameter estimates happen to be independent. So intuitively, that's what's going on here. The math is rather horrible to look at, but I put a copy of this paper up on our website as optional reading, and it is interesting to look at that paper. So this is the total story now. We have asymptotically, we could see that depending on whether or not assumptions are satisfied, one or another of these methods would work well. But then there's this kind of additional fact that Gaussian naive Bayes is going to converge more quickly to its asymptotic error than logistic regression is going to converge. Because this term will go down faster for a Gaussian naive Bayes than it will for logistic regression. Yes? Say that again?
Does it assume that assumption 1 and 2 are satisfied here?
It's a good question. The question was, are we assuming in these formulas that assumption 1 and 2 are satisfied? I believe the answer is no. But I'd want to go back and look at that paper in detail to be sure. But I think the answer is no, because these are really just based on an analysis of the variance in the estimates of the parameters.
Do they have some formula converted into confidence intervals, for example, instead of the big O notation?
Yeah, it would be nice to have a confidence interval on this, and this paper does not give that. Okay, all right, so there's the picture. Now, what happens experimentally if we try this? The same paper, they derived this theory, but then they ran some experiments, and they took a collection of different training data sets from a website called the UCI Data Repository, which you can also access, and it has a lot of function approximation data sets in it. Each of these plots shows two curves training both logistic regression and naive Bayes on one data set. In each plot, here's a different data set. And what you see in many of these data sets is, by the way, the dotted line is logistic regression. And the solid line is naive Bayes. And this axis is number of training examples. And this axis is error, measured over separate test data. So these are essentially the learning curves plotting error, how the error decreases as we increase the amount of training data. And what's interesting is, like, if we look at this first one, you see that when we only have a few training examples, indeed, naive Bayes exhibits a smaller error than logistic regression for this data set. But when we get more and more training examples, then at some point those curves cross, and logistic regression exhibits a lower error than naive Bayes, which is consistent with the expression we just looked at on the previous slide. That even though, in this case, if we extrapolate these and believe it keeps going in the same direction, then we say, well, asymptotically, it looks like logistic regression, which isn't making the conditional independence assumption all the way through, has a better, less biased asymptotic performance, asymptotic in the number of training examples. But when data is scarce, the problem with estimating the logistic regression parameters reliably, the variance that sneaks into those estimates because of limited training data, makes logistic regression actually perform worse from scarce data. And you see that kind of trend in many, not every one of these data sets. But the preponderance of cases, in fact, show logistic regression compared to naive Bayes, their relative performance of logistic regression improving as we crank up the volume of training data. Okay. Cool. So that's what we know. So the bottom line is GNB2 and logistic regression both are restricted to linear decision surfaces. GNB, in fact, is not. It can express nonlinear surfaces. So in that sense, it has a richer hypothesis representation, a richer model space. And therefore, given infinite data, logistic regression is usually better than GNB2, and probably, here I'm not making a statement about GNB because it's kind of an apples and oranges thing, right? But logistic regression can often do better than GNB2 because it's not making the conditional independence assumption other than, once it's made the assumption of the form of the logistic function, from there forward training, it's not building in any more conditional independence assumption. But GNB2 converges more quickly in terms of number of training examples toward its asymptotic estimates that it's going to get if it had infinite data. And so for that reason, it might outperform in the early going when you don't have that much data. And then finally, if you ask, well, what is exactly the, if we talk about GNB instead of logistic regression, what's the relationship between those? It's actually a little murkier because GNB can express nonlinear decision surfaces, whereas logistic regression is restricted to linear. However, in estimating its parameters, logistic regression is not restricted to W sub i's that correspond to some conditional independence assumption. So in practice, my experience is usually if I have sufficient data and a lot of features, I go with logistic regression. And in most, and I usually try them both to see what's going on. But in my experience, if you don't get to try both and you're forced to commit, from the data sets I've looked at over time, logistic regression with a lot of training data is usually a better model than GNB. But you can see that it might not always be that way because there might be a nonlinear surface that you need that GNB can capture. Yes?
So were those graphs GNB2 or GNB1?
Those graphs, the question is, were those plots that we looked at GNB2 or GNB? I think the answer is I don't know, and we should go back and look at the paper. But I'm not even sure that all of those were Gaussian. They might have, some of those might have been discrete valued naive Bayes too. Yes?
Because it's not making these assumptions, does that mean you have more overfitting problems?
Ah, right. So the question is, if logistic regression isn't making these same assumptions, do you end up with more overfitting problems? The answer? Yes. Yes. In fact, what we're just talking about, you can think of as a quantitative characterization of how bad is the overfitting problem. This is the error you can't avoid. This is the overfit. This is what you suffer in terms of accuracy or error in future predictions because of variance in the estimates of your parameters that was introduced by fitting just the limited sample of training data that you have. And the more training data you have, the bigger your N, the smaller that overfitting problem gets. But in fact, the point here is that that overfitting problem decays at a different rate in the two cases. So this is exactly the overfitting problem. All right? Good. So these things are actually really nice as two very useful practical algorithms, but they're also nice as kind of case studies of a generative and discriminative classifier and what are the issues in choosing one or another, and how does that relate back to this issue of overfitting? So that's what I hope you get out of this. Yes?
You said this is a case study of just particular generative and particular discriminative. Does this generalize across for both of those different types?
Yeah, the question is, if these are case studies, do these lessons generalize more broadly? The answer is often the discriminative classifiers work better when you have a lot of data. Let me give another example. We'll talk about this in more detail later in the semester. But when I say these are examples of a case study, what are other examples? Well, one is, what if we have time series data? A series of, let's say, stock prices for 10 different stocks that we're tracking. And we want to label for each of those stock prices its direction the next day. And we have a whole time series system. This is not going to turn out. This example is not the best example I could have made. But there's a generative model called a hidden Markov model that we'll talk about later, which is essentially a time series of naive Bayes classifiers, where the y values you don't actually get to observe. You only get to observe the x's. That's another generative model. And then there's the corresponding discriminative model for that, where you say, I just want to predict the sequence of hidden y values given the observed x's, instead of learning the probability of the x's given y's. So that's another example of a generative discriminative pair. And the details are sufficiently different that this exact analysis does not carry through. But the kind of trade-off that you see does still occur there. Okay, so that's basically what I want to say about logistic regression and about naive Bayes, and them being a pair of classifiers that are generative, discriminative, and the trade-off. So this is important stuff, but we've said enough. So I want to move on to what's going to turn out to be a very easy topic. In fact, the course gets easier as we go, because now you've learned the terminology. You've learned this way of thinking about how we train learning algorithms. And so let's talk about regression problems, another kind of function approximation problem, which, unlike the ones we've looked at so far, now let's assume y is a real value, a continuous variable. Okay, so for example, I might want to predict your weight from your gender, your height, and your age. Well, your weight is a continuous variable. Or the price of Google stock tomorrow based on a bunch of other stocks, and so forth. So there are a lot of functions you might want to estimate where y is real valued. And the approach we're going to take to this is identical to the approach we've talked about already. We're going to follow exactly the same template. We've got a function approximation problem. We've got some x's, and we want to predict a y. Happens to be real valued. That's OK. Let's choose some parameterized form of p of y given x. And then let's derive our learning algorithm just as we did before. And we'll consider again, maybe we'll want maximum likelihood estimates of our parameters for p of y given x, or maximum conditional likelihood, or map estimates. Same story that we went through for naive Bayes, for coin flipping, for logistic regression. And you should be getting good at this. So let's look just at linear regression. So here I have an x and a y. Maybe y is final grade, continuous variable, and x is hours studying, another continuous variable. And we hope that y increases with x, as shown here. But of course, it's not a perfect function, and there are lots of other things that we can't observe. And so we might find two people, both of who studied exactly the same number of hours, and they got slightly different grades. And so the data points that we might have to fit might be scattered around. Still, we'd like to fit a line. So what would be a good probabilistic model? First of all, what do we mean probabilistic here in the first place? Well, let's look at what I just said. We might have two people who exhibit the same x value. I just have one x feature here, which is hour studying. And there's some randomness in the grade that they get if we try to predict it just from hours studied. And so that's one place where randomness comes in. And so if we're interested in characterizing the probability distribution on grades conditioned on hours studied, we might make up the following kind of reasonable, very reasonable probabilistic model. We might say the actual grade, the observed y that you get, is some deterministic function of the amount of hours that you study, plus some other epsilon, which we'll say is some random variable. That's the source of randomness. And furthermore, here I want to assume that that epsilon, that randomness, is just a zero mean Gaussian random variable. So what does that mean? That means for any given x, let's choose this x, studying exactly 5 kilohours, then what this model says is, for that x, there's a probability distribution, which is Gaussian, around values of grade that we're going to see, and that the grade we're going to see is a Gaussian distribution, because that's what epsilon is here, centered around the deterministic linear function f of x. And so essentially this is kind of the picture of what this probabilistic model is saying. Right? So it's saying, you give me an x, like 5 kilohours, and I predict a y. Well, if you want, actually I can predict a whole distribution of y's. I can tell you the most probable value is just f of x. But there's also some variance in that value. It's actually a whole Gaussian distribution. There's some sigma on that. Where's the sigma come from? Well, right here, obviously. Okay? So this is going to be my probabilistic model. This is a very common probabilistic model for making sense out of regression problems. And you see, it's kind of sensible. Like if I'm trying to predict some variable and I have noise in my measurement of y, and x really is some, y really is some function of x, but my observed y's are noisy measurements, then maybe I use this kind of a model. Or if y is some function of a bunch of variables and I only have a subset of them, like it's more than the number of hours you study. Also depends on what you knew coming into the course and stuff like that. Then I get a similar kind of effective befuddlement or uncertainty that I can reasonably model this way. Yes?
So is, for our purposes, epsilon is really always going to be given to us, or is there a good way to learn epsilon?
So we're going to, the question is, are we assuming that we're given epsilon, or are we going to learn it? And the answer is, we're assuming we don't know epsilon. But we will assume that epsilon is drawn from some zero mean Gaussian distribution. That's the assumption we're going to make. So that's it. That was a great question. So I'm going to even put it here. Unknown. Known. So we do know that it comes from a Gaussian distribution. We just don't know what the epsilons are going to be. And then we assume, okay, this is how, this effectively makes y into a random variable, right? Because given x, if f of x is deterministic, but epsilon is random, and so if we add a random variable to a deterministic variable, we get another random variable. And now this random variable will follow what distribution? Well, it'll be this distribution. It'll also follow the normal distribution with variance sigma, but of course it won't be centered at 0, it'll be centered at f of x. Okay? So this is our form of p of y given x. That was step 1 in the two-step process. We make up some probabilistic model that kind of fits our intuitions about the problem. We get a functional form for p of y given x. You can remember the functional form for a normal distribution, a Gaussian distribution. Plug that in, we've got now a functional form for p of y given x. And that distribution will have, well, it depends on how we're going to represent f. Now we've still got to say how we're going to represent f. In this case, if it's linear regression, then we say f of x is just some w0 plus w1 times x. It's just a linear function with some slope and intercept. And so now if I plug that in for mu, I'm all set. So now I say p of y given x is some normal distribution with that mu, that's that mean, and with sigma as its variance. And now I want to train. I have some training data like the points shown here. What does that mean? Well, that means I want to estimate these parameters, sigma, w1, and w0. I want to estimate those from the training data. And now if we back off to our usual question like, what's the relationship we want between our estimates and the training data? Then again, we have our usual candidate answers. We'd like the maximum likelihood estimates, please. Or we'd like the map estimates under some additional assumption about a prior. But now we're off to the races. This is exactly the same stuff we've talked about before. So you see what we're doing is we're taking a new problem, we're mapping it again into, let's make a probabilistic model of py given x, make some assumptions that kind of justify it, and now design ourselves a learning algorithm to get, well, let's start with the maximum conditional likelihood estimates of these parameters. All right, so how does that go? This just says what we wrote on the slide. Okay, so now it actually gets interesting. So we've got this probabilistic model, and now we want a learning algorithm that will, let's say, give us the maximum conditional likelihood estimate of the parameters. And again, that's just a multisyllabic term for a simple idea. We want the parameters that make the y's, the observed training label y's, given the training x's. We want the parameters that make those y's the most probable that they can be. And if you can find a better set of parameters that make the probability of my observed y's given my observed x's better, then I'm going to take yours. And we're going to take the maximum conditional likelihood. Okay, so we write down our likelihood formula. That's just the probability of the L here is, again, the ELF training example. And so if we want the likelihood of our training data given our W's, well, that's just, if we assume each of our training points here, those different dots, are independent, identically distributed according to this P of y given x, then the conditional likelihood is just the product over all those independent training examples of the probability of their observed y given their observed x and our parameters. Or equivalently, we can take the sum of the logs because maximizing that, of course, is the same. And then here I've just expanded out what it means to be a Gaussian distribution, a normal distribution, whose mean is the deterministic f of x. Okay. So now there's our expression. If we want the maximum conditional likelihood solution, what can we do? We could do the same thing we did for logistic regression. We could find the derivative of this conditional likelihood with respect to different weights w sub I. And once we have those derivatives, we can do gradient ascent, just like we do for logistic regression, to maximize the conditional likelihood or the log of the conditional likelihood by choosing the w's that maximize it. And that's exactly what we'll do. In fact, it's beautifully, there's a beautifully simple thing that's going to fall out here. So don't be concerned about the number of symbols in this one expression. Okay, so now, again, what I want to do is, well, let's work with the log of this thing first. That's the log of this thing is just the log of this quantity plus minus a half times y minus f over sigma squared, right? So what I've done is I've taken the fact that the log of a product is just the sum of the logs, and then the log of this quantity is just its exponent. Right? Okay, so now I want the derivative of that thing. Derivative of the log of p of y given x and w with respect to what? Yeah, w. Well, with respect to each wi. And so the first thing I'm going to point out is that this first term doesn't even depend on wi. So its derivative is 0. The second one, I'm going to expand this out. Right? F is, we agreed, just this linear function of x. And so if I want this, let's say, with respect to w1, then what do I have? Well, freshman calculus again, right? The chain rule in freshman calculus tells you that the derivative of this complex thing with respect to wi is the derivative, let me call this thing z. Then that's the derivative of this complicated thing, let's call the complicated thing, with respect to f times the derivative of f with respect to w1. Chain rule of freshman calculus. And so what does this become? Well, the derivative of this whole complicated thing with respect to f is just 2y minus f over sigma. Is that right? Oh, sorry. Good thing it's 2 times minus 1/2 times 2 times. Did I get that right? Oh, I see. Yeah, let me... Yeah, times minus 1 over sigma. That's what you said, right? Did I get that right?
I mean, you keep the sigma, you keep
Okay, thank you. Okay, good. Times the derivative of f with respect to wi, which is just x. Okay? So that's my derivative of this thing with respect to w1. You can do a similar thing with respect to w0. But basically what this says is the change I'm going to make, the slope of this conditional likelihood with respect to w1, is just, I left out the sum over training examples. It's just the sum over training examples of this quantity, which essentially is saying for any given y, if I predict it perfectly, then the derivative is going to be 0. Or the contribution from that training example, if I predict it perfectly, is going to be 0. But if I predict it wrong, then the magnitude of this derivative is going to grow with the magnitude of my prediction error for that y. And it's also going to depend on how big x was. Okay. So it's very sensible. And here's another way of looking at it. This is actually really cool. Look at this thing. This says if we want to find the argmax of our conditional likelihood with respect to w, since it doesn't even depend on that, the log of it doesn't even depend on that. It doesn't even depend on the first term. The second term is just essentially the sum over all the training examples of the squared error in our predictions. So let me put back in my, I need my training example superscripts in there. But essentially what this is saying is, if I want to optimize p of y given x, what I want to do is minimize that term in the box, which is the sum of squared errors that my regression makes, over all training examples x of L, x super L, and y super L. And this is actually really nice. So basically what this is saying is to argmax over w, the conditional likelihood, the log conditional likelihood of y given x, we want to argmin over w, the sum over our training examples of the difference between the example and its predicted. I'll write this more readably. We want to argmin this equals argmin over w of the sum over our training examples L of YL minus f of x squared. It's this term. So by minimizing this sum of the squared errors that I make on the training examples, which I can do by doing gradient descent. Pardon me?
You don't need the gradient descent because this derivative is linear in the W's. So you can just make them into a linear equation system.
Right. Well, I could use gradient descent, or there are matrix ways of solving this too. But one simple thing I can do is use this gradient descent or some other matrix algebra if I prefer to minimize the sum of squared errors that my prediction makes over the known training example XY pairs. And doing that is exactly equivalent to getting the maximum conditional likelihood estimates of W. So that's a very nice and general thing. In fact, that's true even if it's not a linear function. To show that it's just this sum of squared errors, I didn't actually have to flesh out what's the form of f. It just falls out of my assumption about the probabilistic model involving my observed y being some deterministic f of x plus a zero mean Gaussian noise. If that's the case, then minimizing the sum of squared errors over the training examples equals maximizing the conditional likelihood of the data. So that's one reason why you'll see in many treatments of linear regression, polynomial regression, neural network training, you'll see people minimizing training to minimize the sum of squared errors in regression problems. And if you're ever in an elevator and somebody asks you, hey, do you know why they try to minimize the sum of squared errors when they do regression? In one elevator ride, you can now explain to them. It's because underneath that, there's this probabilistic principled idea that they really want to maximize the conditional likelihood of all the observed y super L's given the x super L's. And it turns out the simple way to do that, because the two are equivalent, is to just minimize the sum of squared errors. And then the elevator door will open, the person will leave, and they'll say, wow. So, but it's that simple. Okay, so I've got a couple more slides that allowed me to take this apart in more detail, but we ended up doing it all on the first slide. Apologies for my slip on freshman calculus. But here's the big picture then. So if we make the general assumption in regression that the P of y given x we're going to model as some normal distribution whose mean is some deterministic function of x, like in our case, just a linear function of x, plus some sigma, which comes from this presumed zero mean sigma variance Gaussian noise, then in general, the maximum likelihood estimate corresponds to minimizing the sum of squared errors over those training examples. The map estimate, which we skimmed over, but we'll cover on Thursday, involves getting a prior in there on the form of the weights instead of just getting a maximum likelihood estimate. And a typical prior is just to put a Gaussian zero mean prior on each weight, saying all other things being equal, it's most probable that the weight is 0, but we'll put some variance in there to allow other things to happen. If the training procedure actually will benefit, if the overall conditional likelihood will benefit, then we'll allow that. But most importantly, maybe, what we've just seen is, again, another instantiation of the same template. So when we have a learning problem, which is a function approximation problem, whether that involves discrete x's or real-valued x's, discrete y's or real-valued y's, we've seen them all now. The general template that we follow is we say, well, let's make up some probabilistic model of what we think either the joint distribution of pxy will be, or at least the conditional distribution of y given x. That's what we just did again here. And then, really, we're going to think of learning as an optimization problem. Learning means, given some training data, estimate the parameters of this function. And estimate them, what does that mean exactly? Well, we're going to define that as an optimization problem. Either we're going to try to optimize the likelihood, or the posterior, the map estimate, which corresponds to the posterior probability of the weight given the priors on the weights plus the data. or the conditional likelihood of the data, but we make up some objective function, one of those three so far. And then we've just got ourselves a standard optimization problem. How can we solve for the set of parameter values that optimize that objective? So that's the big surprise about the first third of the course in machine learning. Secretly, machine learning is all an optimization problem so far. Function approximation. Remember our big picture? We had some data. We had this Venn diagram of hypotheses. We wanted to find the right hypothesis. Then we got into this discussion about what does it mean to be the right one. And so far, our answer is maximum likelihood, maximum conditional likelihood map under some priors or without the priors in the case of just maximum likelihood. But essentially, we're saying there's some hypothesis space or class of possible models. We've got to make up an objective. And then the training procedure is an optimization procedure for finding those. And we also know some of the tricks of the trade now. We know that there's this lurking overfitting risk. And we know that the complexity of the class of models that we consider, the variety of hypotheses that can be expressed, the bigger that grows, the greater our danger of overfitting. But the smaller it grows, the greater our danger of a biased hypothesis coming out, one that doesn't actually capture, that because the learner can't even represent the true hypothesis. So that's the big picture we have so far. And that's actually the most important thing pre-midterm to understand. If you understand that, you're going to be able to make sense of everything else we do in the course. You're going to be able to predict a lot of what we do in the course. So focus on that and get that right. All right, see you next time.